Okay, if we look into the static condition, and the static condition you feel when you ride along with the gas at local velocity v. In contrast, the total or stagnation condition was defined as the condition existing at the point in the flow where velocity equal to zero. All right, so there's a two condition here. One is that you ride along with the gas at the local velocity v, or in contrast, if you uh, experience a point in the flow where the velocity equal to zero. So in this, it is being represented in this particular simple diagram, right? So where we have a static condition, the condition field when right along the velocity, where the condition in stagnation, the condition field when the velocity equal to zero. So you imagine that at position number 1, right, where you have velocity v, right, the pressure, the temperature, the enthalpy, the density, the Mach number, and the velocity at this particular position v1, and the velocity brought down to zero. We slow down the movement, the vehicle or the object to a stagnation condition, right, where v2 equal to 0, where we have the pressure at zero condition, p0, t0, h0, rho 0, and Mach number 0, as well as the velocity also 0. So in this particular, the temperature or the value of the temperature of the fluid element after it has been brought to rest, 0, adiabatically is defined as the total temperature. So from V1 to V2, right, the temperature associated is, we call it as the total temperature, T0, right? The corresponding value of the enthalpy, the H, as the total enthalpy, H0. Okay, this is the H0, where H0 equal to the specific heat capacity at constant pressure times the total temperature, the T0, for a calorically perfect gas condition, right? So I would like you to really understand about the using this basic diagram, V1 to V2 for movement to condition stagnant, right? The T0 is now total temperature, H0 is the total enthalpy, and H0 is then equal to the CPT0, specific heat capacity at constant pressure, times the total temperature T0. And this is only applicable for perfect gas condition. Okay, so then we look into the energy equation. The energy equation then provides some important information about the total enthalpy, the H0, and hence the total temperature, the T0, as follows. So you can have the expression here, okay, which is equal to this expression. I don't think I need to pronounce every single expression there, where we assume that the flow is inviscid. It means that adiabatic, where no heat transfer to or from the system, which is equal to 0, and the body forces are negligible. The F is also equal to 0. For such a flow, equation becomes the density times d times E energy plus V squared over 2. This is the kinetic energy, over dt equal to the inverse change of the pressure times the velocity, sorry, the volume. So you solve this equation, right? You solve this equation, we have this expression, and then we can move into this, where if the flow is steady, the change in pressure over the change in temperature at time equal to 0, and the equation becomes this expression. And from the definition of the substantial derivative, a small flow, right, the equation states that the time rate of change, okay, of the enthalpy plus the square of the velocity over 2, right, the kinetic energy, following a moving fluid element is 0 along streamline, that is expressed in here, where the enthalpy plus the v squared velocity squared over 2 equal to constant. Since the total enthalpy is defined as the enthalpy that would exist at the point if the fluid element were brought to rest. You want to relate back to the diagram that I showed just now earlier, where adiabatically when the velocity equal to 0, then the enthalpy equal to the total enthalpy H naught. We show the value of the constant in the equation, which is H naught, where constant equal to H naught, and thus the equation, the above equation, can be expressed as here. H enthalpy plus velocity squared over 2 equal to the total enthalpy, right? And this equation is important. This expression, it states that at any point in the flow, the total enthalpy is given by the sum of the static enthalpy plus the kinetic energy, all per unit mass. And thus, this can be rewritten and you can get this expression. And this show the total enthalpy is constant along a streamline. Then the total enthalpy H naught is the same for each streamline. H naught is equal to constant, right? And for a calorically perfect gas, right, where total enthalpy H naught equal to the specific heat capacity times the total temperature T naught, thus it's also state that the total temperature is constant throughout the steady inviscid adiabatic flow of a calorically perfect gas, then T naught, or the total temperature, equal to constant. And return to the beginning of this section, where we considered a fluid element passing through a point from point 1 to point 0 in a flow where the local properties P, T, rho, M, and V, the velocity, let us slow the fluid element down to 0 velocity adiabatically, okay, and reversibly in terms of isentropic. When the fluid element is brought to rest, isentropic, the resulting pressure and density are defined as the total pressure P naught and the total density rho naught are then constant throughout the flow. Alright, so this is the definition of total stagnation conditions. So this can be shown in these figures. There are 4 figures here, A, B, C, and D. In the first diagram here, if you can look into this non-adiabatic flow. So where non-adiabatic flow, if the flow is moving from position 1 to position 2, right, basically the total enthalpy at position 0 to 2 is not the same as the total enthalpy at 0, 1. Okay, so this 02 H02 is not the same as H01. So this is for non-adiabatic flow. Similarly, the total temperature at position 2 is not the same as total temperature at position 1. Okay, compared to an adiabatic flow, right? For adiabatic flow, where the total enthalpy at position 2 is the same as total enthalpy at position 1. H02 is equal to H01, and total temperature at position 2 equal to total temperature at 0, 1. Okay, so you can see that this is for non-adiabatic flow, which is not the same. For adiabatic flow, it is the same. Whereas for the non-isentropic flow, it is similar to the non-adiabatic flow, where if we look at the pressure at position 2 and position 1, which is not equal, and the density is also not equal for station 2 and station 1 for non-isentropic flow. Whereas for isentropic flow, the pressure and the density are the same at station number 2 and station number 1. When the flow is flowing from position 1 and 2, it is the same for pressure and density for isentropic flow, where for adiabatic flow, the enthalpy and the temperature is the same. This is not happening in non-adiabatic flow and non-isentropic flow. Right. Let us look into a simple example. This example is taken from the Anderson book. Okay, so you can also look into the explanation in Anderson book. So example being given here at a point in an airflow, the pressure, the temperature, and the velocity, the P, the T, capital T, and the V, velocity are 1 atmosphere, 1 atm, 320 Kelvin, right? And the velocity of 1000 meter per second. So what you need to find is that you need to calculate the total temperature. Total temperature is the T naught, and not the temperature. This is the temperature given, but what is the T naught, and what is the total pressure? What is the P naught at this particular point, at the point in airflow condition of here. So from the earlier equation, we have an equation where the enthalpy, H plus the velocity squared over 2 equal to the H naught, and the total enthalpy. Since the enthalpy itself, the H equal to specific heat capacity at constant pressure times the temperature, and the Cp itself is being denoted by the rho R over rho, sorry, not rho, this is a what do you call it? Is it gamma, right? So minus 1. So we have Cpt plus V squared over 2 equal to Cpt naught, and you solve this equation, right? You put into the numbers 320 temperature, and then you have the velocity squared, right? And then you put inside the value for the rho over there, 1.4 for air. Okay, you can get the total temperature to become 817.8 Kelvin. So this is the total temperature. So this is the first answer for total temperature. All right. And then following to that, for the calculation for the pressure, right? So by definition, the total pressure is the pressure that would exist if the flow at the point were slowed isentropically to zero velocity. Hence, we can use the isentropic relations, right? So we can relate back to the isentropic relation to static condition, and that is from this expression, right? The isentropic relations. Hence, we get we use 1 atmosphere, and we have the total temperature just now, T naught. We have the temperature, okay, and we can get now the total pressure, P naught, 26.7 atmosphere. So in this particular calculation of total pressure, we continue to use the non-consistent unit of atmosphere, right? So this is okay, because in the isentropic relations, equations contains a ratio of pressure. So therefore, it would be just extra work to convert the normal 1 atm, 1 atmosphere, to the normal unit, SI unit, Newton per square meter, 1.01 times 10 to the power of 5. This is not 105. This is 10 to power of 5 Newton square meter, and then carry out the calculation. So you will get the same result. Alright. So that is the first example that related to how to calculate the total temperature as well as the total pressure in the case of stagnation conditions. Okay. Right. Let us look into example number 2, right? With respect to the stagnation condition. This is also the example I took from the Anderson book. Okay, so in the case of an airplane, we have an aeroplane flying at a standard altitude of 10,000 feet. Right, so somehow in the version that we have, the book that we have, they are using the imperial units, not the SI unit, but it is you can easily convert that. So we have at 10,000 feet, a pitot tube mounted at the nose measures a pressure of 2,220 pound per square foot. Alright, so the airplane, which is flying at high subsonic speed, which is faster than 300 miles per hour, okay, and the flow should be considered compressible. You need to calculate the velocity of the airplane, the aircraft. Right, so how to calculate the velocity of the aircraft? So let us look into the condition here. The pressure measured by a pitot tube immersed in an incompressible flow is the total pressure. For the same physical reason, which as discussed, a pitot tube also measure the total pressure in high-speed subsonic compressible flow. Be aware, caution over there, because we are dealing with compressible flow in this example. We cannot use Bernoulli's equation to calculate the velocity, which we have already covered in our previous session before we have our break earlier. Okay, right. So the flow in front of the pitot tube, which is compressed isentropically to zero velocity at the mouth of the tube, hence the pressure at the mouth is the total pressure, P naught, right? Because we have a condition where the flow is moving from 1 to 2. The 2 is where we have stagnation point, stagnation condition, where we have the total pressure, P naught, where velocity equal to 0. So we can then write this expression, the ratio of P naught over P infinity. So, and where P naught and P T naught are the total pressure and total temperature, respectively, at the mouth of the pitot tube. And P infinity and T infinity are the free stream static pressure and the free stream static temperature, respectively. Solving this equation for T naught, we rearrange this to get the T naught, and we get the T naught expression as here. Alright. So using information from Appendix D, if you look at the Anderson book and go into the appendix at the behind of the book, right? So you have a table for standard atmospheric air values, okay, at various altitude. So in this case, the airplane or aircraft is flying at 10,000 feet. So you look at 10,000 feet where the value of the density, at 10,000 feet, the density is 1.4556, so which is the value of the density, okay. And then we have the temperature. The temperature is given in Rankine, right? So as I said, this is using imperial unit, all right? So these are the values of the free stream pressure as well as the free stream temperature in the above the previous equation. So thus, putting the values in, you then obtain the total temperature T naught, 544.9 degrees Rankine. All right. Okay, so I think I got it wrong over here. This is not 1455. This is 1.4556. So a wrong point over there. Okay, to find the velocity, free stream velocity from the energy equation, so we have the CPT plus the V velocity squared over 2, we get CPT naught, and in the above equation, both the temperature and the velocity are the free stream values, and so then we can have this expression putting in the value for T as a free stream and value for velocity as the free stream value. Also, we can have this expression. We get the value for the specific heat capacity at constant pressure. Solving above equation for the value of velocity at free stream, you can then get 862 feet per second. Right? So actually, you can try this example yourself using the metric information. So you can put up the SI values for the velocity, for the pressure, for the temperature. So and if you convert it back, and you will get the same value over here. From this example, we see the total pressure measured by a pitot tube in a subsonic compressible flow is a measure of the flow velocity, but we need also the value of the flow static temperature in order to calculate the velocity. So I would highly recommend that you go through the exercise yourself, but using SI unit, and then you would appreciate the steps that I have already shared just now. Okay? Right. We are now going into the last part of the introduction, which is related to the aspect of supersonic flow as in terms of the shock wave. Okay, I've shown this in our last week overview of the topic on compressible flow aerodynamics 2. But again, I would like to go through it again, where we are going to go into the shock wave. Right? A shock wave is actually an extremely thin region, typically in order of 10 to the power of minus 5 centimeter, which is very thin, which across which the flow properties can change drastically, right? From one region to another region, from outside the shock wave or within the shock wave, the flow properties can change drastically, right? So we have the regime over here: low subsonic, okay, high subsonic, transonic, supersonic, and hypersonic, right? We have the range of Mach number less than 0.3, from 0.3 to 0.8, which is compressible. Less than that is incompressible, where density is constant. Beyond that, density is no longer constant. There's an effect of energy, right? 0.8 to 1.2, there are shock wave happening, right? And Mach more than 1.2, also there are shock wave and Mach more than 4, where we have aerodynamic heating and plasma. Okay, so I think I have already explained this before. For subsonic flow, right, you can less than Mach number 0.3, right? And then for transonic flow, the free stream Mach number is less than 1. Okay, you can see that there are region of Mach more than 1 on above the the airfoil, okay, and below the airfoil where you have Mach number more than one. For an airfoil, there will be a bow shock, appearance in front of the uh, um, airfoil shape, okay, where we have a region of Mach number less than 1 and a region of Mach number more than 1 that resulted to a trailing edge shock. At the trailing edge of the airfoil, you can see trailing edge shock. Meanwhile, for supersonic flow, which is Mach more than 1.2, right, you will be seeing shock wave. For a shape like a diamond, a triangle over here, right? So you can see shock wave being occurs over there where the flow is behind the shock wave. The flow is more Mach number more than 1, and you can also see expansion wave developing at the end of the object. For hypersonic flow, where we have thin hot shock layer, where this is happening at a very high speed vehicle, Mach number more than 4, right? Where we have hot shock light layer with viscous interaction and chemical reaction. All right, so we will be seeing this more when we go into the detail of examples. So the essential ingredients, when we say that the properties change for certain situation across the shock wave, right? Even though it is a very thin layer, right? Is the calculation of the shape and strength of shock wave. So we want to look at the what are the shape of the shock wave and the strength of the shock wave. This is the main thrust of chapter 2 and 3. Now we are in still chapter 1, introduction. When we go into the following chapters, we look at a normal shock as well as the oblique shock. So these are the topics that we are going to cover later on. And the shock wave is usually at an oblique angle to the flow. It's not at the right angle. It's an oblique angle, such as being sketched in figure A. This particular figure, okay, we have an oblique shock wave. So we have the flow going through and then hit a surface over there, and we have the shock wave. So this is a condition over here at condition 1, where Mach number is more than 1. Okay, right afterwards is Mach number less than Mach number at station 2, right? It is less than Mach number at station number 1, and you have the values for the velocity, the pressure, density, temperature, entropy, okay, and then we have the total pressure and total enthalpy. So you can see here for oblique shock wave, right? So the changes of properties over here, like for enthalpy, which is equal to the station number 2, but for the total pressure, which is the station number 2, is less than station 1, and so on. So you can see that we will look into more detail about the conditions for oblique shock wave, right? However, there are many cases where we are going to be interested in shock wave normal to the flow, which is sketched in figure B, right? In this case, it is normal shock wave, right? Where in this case is oblique shock wave. So those conditions are also being listed down there, right? You can see whether the conditions are similar, or there are different in terms of the property change. So in both cases, the shock wave is an almost explosive compression process, where the pressure increases almost discontinuously across the wave. So you can see here A and B, we have the real changes in the properties. All right. So these are some photos. Probably you can also refer to the Anderson book to look at some these photos, which is a shock wave as shown. And since air is transparent, so it's quite difficult to see it by naked eye. So you cannot see it because it's quite fast, and you cannot really see the density change in the flow. That's why we use different technique. So because of the density change across the shock wave, light rays propagating through the flow will be refracted across the shock. Special optical system maybe such as shadowgraph, Schlieren technique, and interferometers take advantage of this refraction of the flow through the density and the dense flow field, okay, which then allow the visual imaging of shock wave on a screen or a photographic negative. So we have our own small supersonic tunnel at our facility in University Putra Malaysia, and we are using shadowgraph and Schlieren in order for us to capture the shock formation. So even though our test section is very small, 1 inch by 2 inch section, but that is sufficient enough to show that the development of the shock wave can be captured through shadowgraph or Schlieren technique, right? But it is quite tough. You need a very special camera, high speed camera, and you need to have a very good lighting as well as to capture the moment of the shock development. All right. Okay, so that leads us to the summary. We have already gone through from last week about overview, brief review of thermodynamic, definition of compressibility, governing equation of inviscid compressible flow. We had gone through some example, two example on definition of total stagnation condition and some aspect of supersonic flow, just to introduce to you what are the expected topics and subtopic that we are going to cover in the near future. We will be covered in week number 3 later on. So as a summary, this is also taken from Anderson book. We have thermodynamic relations. Maybe you want to make sure that you are familiar with the equation of state, right? So for a calorically perfect gas, the energy is equal to CVT and the enthalpy equal to CPT. So the expression for CP and CV, which forms the first law of thermodynamics, then it follows by the definition of entropy, right? And the second law of thermodynamics, okay, for an adiabatic process, what happened, okay? And entropy changes can be calculated for calorically perfect gas. So these are the expression for isentropic flow, isentropic relations. Okay, general definition for compressibility, the tau, and then for isothermal process, tau T, and for isentropic process, the tau S over there. Okay. And governing equation for inviscid compressible flow, we have the continuity equation, the momentum equation, the energy equation, right? The three equations that are being used to find the effect of compressible flow. And then if the flow is steady and adiabatic, right, this equation can be replaced by the total enthalpy, which is equal to constant. And then we use equation of state and internal energy equation, right? as a summary, right? The total temperature, T naught, and total enthalpy H naught are defined as the properties that would exist if in our imagination we slow the fluid temperature at the point in the flow to zero velocity adiabatically. Similarly, total pressure P naught and total density rho naught are defined as the properties that would exist if in our imagination we slow the fluid element at the point in the flow to zero velocity isentropically, right? If a general flow field is adiabatic, right? We have the total enthalpy is constant throughout the flow, which is in contrast if the flow field is non-adiabatic, the total enthalpy varies from one point to another. Okay, this is one point that you need to understand. Similarly, if a general flow field is isentropic, the total pressure P naught and the density rho naught are constant throughout the flow. In contrast, if the flow field is non-isentropic, okay, the P naught and rho naught vary from one point to another. You may refer back to the four diagram, A, B, C, D, that I showed the flow from one position to another position, whether it is adiabatic or non-adiabatic, isentropic or non-isentropic. And finally, shock waves very thin regions in supersonic flow across which the pressure, density, temperature, and entropy increase. Okay, and the Mach number, the flow field, the total pressure decrease, and the total enthalpy stays the same. Okay, so with that, that's wrap up our introduction section, right? So you may want to refer back to the notes. You want to reflect back on what you have understand from the topic overview until the summary just now, and so that you can be prepared on to go into the more interesting topics